In this video, I'm going to be showing you easy steps on how to derive your Carnot cycle formula by just looking at the Carnot cycle diagram and the TS diagram. This video is going to be very helpful if you're solving a Carnot cycle problem that involves just two pressures, the high pressure P1 and the low pressure P2. Now, let's start by looking at the Carnot cycle diagram itself. Now, the Carnot cycle diagram comprises majorly of four components. We have the boiler, we have the expander, we have the cooler, and we have the pump. The function of the boiler is to supply heat to the system or add heat to the system. Hence, you see Q1 or Qx being heat supplied. The function of the expander is to remove work from the system. Hence, you see WP. P there means positive. The work removed by the expander is a positive work, or the work done by the expander is a positive work since work is removed from the system.
Now we go to the cooler. The function of the cooler
is to reject heat from the system. Hence, you see QR, R for rejection. And heat rejected by a system is always going to be negative. Next, we move to the pump. The function of the pump is to add work to the system. Hence, you see WN. N there means negative. The work done by a pump is simply negative. Now, if your Carnot cycle problem is given just by pressures, the high pressure and the low pressure without temperatures, it means that all we need to solve our problems on Carnot cycle is going to be the enthalpies. Because with the pressures, you can find the value of the enthalpies using your steam table. Okay. Now, if you look at the Carnot cycle from state 1 to state 2, is heat addition process, and this heat addition is done at constant temperature. So if you look at the TS diagram from state 1 to state 2 is at constant temperature. So the temperature at state 1 equals temperature at state 2. This is what the heat addition process. Now from state 2 to state 3 is the work removal process in the expander, or the positive work done by the expander. And this is done at what constant entropy process. If you look at the TS diagram from state 2 to state 3, if you trace it down, you see it's a constant entropy. So S2 equals S3. Similarly, from state 3 to state 4 is the heat rejection process
by the cooler,
and that is done at constant temperature. So if you look at the TS diagram, from state 3 to state 4, the temperature is constant, T3 equals T4. And finally, from state 4 to state 1 is the work addition process in the compressor, and this is done at constant entropy or adiabatic, as can be seen on the TS diagram. Since we have only pressures given to us, then it means the enthalpy at state 1, we can call that H1. Enthalpy at state 2, we can call that H2. Enthalpy at state 3, we can call that H3. Enthalpy at state 4, we can call that H4. Now, how do you know your formulas if you have been able to identify all your enthalpies? In simple steps. First, when you talk about state 1 to state 2, we talk about heat addition from the boiler. So what we do here is we take the sum of every parameter entering into the boiler to be equal to the sum of all the parameters leaving the boiler. This helps us to find the heat supplied into the working fluid, or the heat supplied to the system. So I have QS, which is heat supplied entering into the boiler. I have enthalpy H1 entering into the boiler. I have enthalpy H2 leaving the boiler. Sum of what is entering equals what is leaving. So I have QS entering the boiler plus I have H1 entering the boiler. This is equal to H2 leaving the boiler. So this simply implies that my heat supplied equation is going to be equal to what? Simply H2 minus H1. And this gives us our heat supplied in the boiler. As simple as this. We move next to the expander. The expander does positive work. So the same theory is maintained here. The sum of all the parameters entering the expander equals the sum of all the parameters leaving the expander. So I have H2 entering the expander. I have work leaving the expander. I have H3 leaving the expander. So sum of what is entering equals sum of what is leaving. What is entering here is simply H2. So for the expander, I have H2. This is equal to, I have my positive work leaving, plus I have I have H3 leaving. So from here, I can make my positive work substitute the formula. Then I'm going to have that the work done by the expander, WP, is going to be equal to simply H2 minus H3. And this gives me the positive work done on the system. It's as simple as this. If I move to the boiler, if I move to the cooler, please. I realized that I have H3 entering into the cooler, but I have Q arrow heat rejection leaving the cooler. I have H4 leaving the cooler, but it will interest you to know that the heat removal from the system is always going to be negative. So since the cooler is rejecting heat, this heat is going to be what? Negative. So simply attach a negative sign there. Heat rejection from the system is negative. So the same theorem is maintained. Sum of every parameter entering equals what is leaving. I have H3, I have H2 entering, I have H3 entering. So H3 equals, now I have heat rejection. Heat is being rejected. So negative Q are leaving. Negative Q arrow leaving plus I have H4 leaving plus H4 leaving. So we simply make heat rejection subject of the formula. So if I send a negative sign over here, if a negative sign cross an equal to sign, it becomes positive. Then I'll simply send H3 over here. Therefore, this gives me that my heat rejection equation is going to be equal to simply H4 minus H3. It's as simple as this. So we have our heat rejection equation. Finally, we move to the pump. Pump adds work to the system. So it is also important for you to know that when work is added to the system, that work is negative. So the pump does a negative work. So we simply append a negative sign there. The pump does a negative work. So the same principle still holds. Sum of everything entering equals what is leaving. I have H4 entering into the pump. I have negative pump work entering into the pump, and then I have H1 leaving the pump. Sum of what is entering becomes H4 is entering. So I have H4 entering minus pump negative pump. Okay, you can simply call that WP for pump work. And that's equal to, okay, we already use P here for positive, right? So we can simply use N for negative, WN. Okay. And that's equal to H1, which is leaving. So I have H1. So if I make my negative work subject to the formula, simply send negative work over here and bring H1 over here. This simply implies that my negative work is going to be equal to what? H4 minus H1. So this is the equation for the pump work. Wn, N there for negative. Wp, P here for positive work, which is the expander work. Okay, now that we've gotten all these equations, question now arises, how then do we get these enthalpies, H1, H2, H3, and H4? That's a bigger question. To find H1, all we need to do is you go to the saturated water and steam table corresponding to the force pressure P1. Corresponding to the force pressure P1, that is where you get H1. H1 is simply HF. HF is equal to H1. Now, why is this so? Now, in the steam table, it is categorized into three. You have properties at the fluid region. You have properties in between. That's a mixture of fluid and gas. Then you have properties at the gas region. Now, this line is a saturated liquid line. This line is a saturated vapor line. And in between is the mixed vapor or the wet vapor, right? In between is the wet vapor, which is a combination of the liquid line and the vapor line. Okay, so on the liquid line, everything is completely fluid. So what is coming here is completely fluid. So if you have your pressure P1, the same pressure P1 governs state 1 and state 2. So from P1, using your saturated water and steam table, you simply go to what? The pressure corresponding to the given pressure, right? Now, HF is going to be equal to what? H1, because everything at that point is completely liquid, as can be seen on the TS diagram. This also implies that since T2 is directly on the vapor line, then it means that my H2 is going to be equal to Hg, because T2 is directly on the vapor line. G there stands for gas, F stands for fluid. So it means that everything on this line is fluid or liquid. So H1 equals HF. Similarly, since T2 is directly on the vapor line, it means it is gaseous. So H2 is equal to Hg at this given pressure.
So let's say the force pressure given to us is 40 bar. So we'll simply come to the saturated water and steam table corresponding to 40 bar, as can be seen on the pressure line here, 40 bar. So we trace now for the enthalpy, HF is going to now be our H1. So the value for 40 bar here is 1087. This is now going to be our H1. Similarly, our Hg is going to be our H2 because this is not directly on the gas or vapor line, and the value here, which is 2801, is going to be our Hg, and that's our H2, right? That's going to be our second enthalpy. So that's how you get the first and second enthalpy if you know the very first pressure for a Carnot cycle question.
Now, where the major challenge student encounters comes in is how to find H3 and H4. And this is very simple. We observe that state 3 and state 4 is in between the wet vapor. So this region is called the wet vapor, which means it is a mixture of liquid and gas. Okay, so since state 3 and state 4 is in between the wet vapor, it means there's a need to find what is called dryness fraction. Okay, it means that you need to find what is called dryness fraction. But before we get into that, to find the enthalpy at state 3, we simply make use of the equation H3 equals HF at state 3 plus H plus X3 multiplies HFG at state 3. So this 3 is just to indicate that we are state 3, or it's simply HF plus X times HF G. Now, X3 means dryness fraction at state 3. Similarly, to find the enthalpy at state 4, we simply use the equation H4 equals HF4. So we're using 4 now because we are state 4 plus X4 multiplied by HFG4. So we need to find the dryness fraction at state 3 and we need to find the dryness fraction at state 4. Why? Because these states occur in between the mixed vapor. So there's a certain level of wetness and there's a certain level of dryness at this point. So we need to get that level of wetness and dryness, which is why we have X3 and X4 here. But the main question now is, how do we get this dryness fraction? Because if we are able to get X3 and X4, it means automatically we can be able to find our enthalpy at state 3 and enthalpy at state 4. Now, to do this, we now employ the adiabatic condition that can be seen on the TS diagram. You observe that state 2 to state 3 is an adiabatic process, constant entropy process, which means S2 is equal to S3. And if we have said that at state 2, H2 is equal to Hg, this also means that at state 2, entropy at state 2, S2 is also going to be equal to what? Sg. Entropy at state 2 is going to be the entropy at the gas region under the same pressure.
So now under the same pressure, 40 bar, we now move straight to the entropy line. Sg is going to now be our S2. So the value of Sg here, which says 6210, is now going to be our S2 because this is now the property at state 2. So the pressure P1 governs everything at state 1 and state 2. This also means that X1 is going to be equal to SF, right? It means that S1 is going to be equal to SF. Recall earlier we said HF is equal to H1. So that also means that S1 is going to be equal to SF. So this value 2.797 is going to stand in as our X1. Okay.
So all we do is simply go to the saturated water and steam table corresponding to the first pressure. Now the entropy at that given pressure is equal to what taken as S2 because it is occurring, state is occurring directly at the gas region or directly on the vapor line. So if we are now employing this, we know now that S2 is equal to S3. What then is S3? Entropy at state 3, S3 is going to be equal to still this same equation, but now we're using what? The entropy as a parameter. So instead of HF, this becomes SF3 plus, instead of X plus X3 multiplies, instead of HFG, this becomes SFG at state 3. So this is very easy. So if this is my entropy at state 3, I know that S2 is equal to S3. What do I simply do? I will simply equate this to what? The value of S2. And S2 has a value. If I know this pressure, I can find the value of S2 by simply going to the what? Saturated water and steam table corresponding to this pressure. The value of Sg at that point becomes S2. If I know it, I simply equate this together. Then I can easily find SF. Now, SF, we are now at state 3. This pressure P2 governs state 3 and state 4. So SF simply means the value of this the value of entropy at this pressure at the liquid line. So I will simply go to the saturated water and steam table corresponding to this second pressure. The value of SF corresponding to this second pressure becomes my SF3. Similarly, the value of SFG corresponding to this second pressure becomes my SFG3. So these values are known from this pressure, and I already know what S2 is. With this, I can now make X3 subject of the formula and get my dryness fraction. If I get my dryness fraction, the equation is going to now be X3 is simply going to be equal to, this becomes S2 minus SF3 all over SFG3. So with this, I can find my dryness fraction. Once I get my dryness fraction, I'll simply come back to this equation and plug the value of my dryness fraction, knowing fully well that HF3 is simply HF under the same pressure, because now we are state 3. So HF3 becomes HF under pressure P2. So I will simply go to saturated water and steam table corresponding to pressure P2. The value of HF is taken as my HF3. Plus, I have simply append my what? Newly found dryness fraction X3 multiplied by HFG. HFG3 now is HFG corresponding to the same pressure P2 under the saturated water and steam table. So if I do that, I can now be able to find my what? H3. It's as simple as this.
So let's say for the second pressure, we are given P2 to be 1.0, a pressure whose value is 1.0. Now, this is now governing state 3 and state 4, knowing fully well that state 3 and state 4 is actually what? At the mixed vapor, right? So we are going to basically be working with the properties at the fluid and the properties at the in between FG, yeah. So for the enthalpy, so you have the value there 417 for HF. Now this HF is now going to be HF at state 3 if we are considering state 3. So the value is 417. Meanwhile, HFG is 2258. Now this value is going to be termed HFG3 because we are at state 3, right? Similarly, our SF here is going to be SF3. This is 1.303. So this is now going to be SF3. SFG is going to be SFG3, and the value can be seen there 6.056 kilojoules per kilograms Kelvin. So when we get to state 3, since we are not talking about mixed vapor, we now basically work with HF and HFG. Then we use the subscript number to denote the states. Since at state 3, HF becomes HF3, SF becomes SF3, HFG becomes HFG3, SFG becomes SFG3. But interestingly, these values are the same for state 4 because the same pressure governs state 4 and state 3. That pressure P2 is the same pressure for state 4 and state 3. But the only thing we are going to be changing now is that when we move to state 4, we no longer say HF, rather we say HF4. And HFG becomes HFG4. But the values are the same thing because they can still be found under the same pressure P2 equal to 1.0. Right, so HF now becomes HF4, but the value still remains 417. HFG becomes HFG4, the value still remains 2258. Similarly, SF becomes SF4 and SFG becomes SFG4, having the same value. So pressure P2 operates or governs state 4 and state 3. The only thing that makes a significant change that can affect the value of the enthalpy at state 3 and state 4 is the dryness fraction. When you find the value of the dryness fraction at state 3 and at state 4, then that will not play a major role in determining the difference between the enthalpy at state 3 and the enthalpy at state 4.
Similarly, if I move to state 4, you observe as well that state 4 is also what? Adiabatic or isentropic. State 1 to state 4 is adiabatic, so which means entropy at state 1 equals entropy at state 4. So if I say that my H1 is equal to HF, that means that my S1 is also going to be equal to what? SF from the first pressure. Remember, the first pressure governs state 1 and state 2. So from saturated water and steam table, corresponding to pressure P1, the value of SF automatically becomes what? My S1. It's as simple as that. So which means S1 is now a known value. And if S1 is a known value, how then do I find S4? Still maintain the same equation. For S4, S4 is still going to be equal to SF4 plus X4 SFG4. Still the same equation. So interestingly, you have to understand now that since we are using the same pressure for state 3 and state 4, it means that what I found as SF3 is going to be the same value as what SF4, because all I need to do is simply go to the saturated water and steam table corresponding to the second pressure. SF at that point becomes my SF4. So SF4 and SF3 have the same value. Similarly, SFG4 and SFG3 has the same value. The only thing that is playing a major role now is what the value of the entropy, S1 and S2. Of course, S2 is different from S1. So that is now going to play a role in the dryness fraction. Okay, so once I'm able to get all of this, I will simply make my dryness fraction X4 subject, and that becomes S4. That becomes, remember, this is equal to S1, please. This is equal to S1 isentropic condition. So that becomes S1 minus SF4 all over SFG4. And I get my dryness fraction as state 4. Now, once I get this, I will simply plug into this equation for enthalpy, and then I know what my HF4 means. The same thing, HF3 is going to be equal to HF4. HFG3 is going to be equal to HFG4 because they are governed by the same pressure, P2. So the only thing that is playing a significant role now is what? Dryness fraction. That's what is playing a significant role. And if you watch, dryness fraction cannot, please keep this in mind, the dryness fraction cannot be greater than 1 for gas. It cannot be greater than 1. So it means that dryness fraction at this vapor region is simply 1. On the fluid region, dryness fraction is simply 0. But in between, it is a fraction. So you see that since state 3 is close to the vapor line, it means that your dryness fraction is going to almost be equal to 1, maybe 0.7, maybe 0.6, maybe 0. Something, just something, maybe 0.8, close to 1. But then since state 4 is close to the liquid line, it means that I'm going to be having a small dryness fraction at state 4, probably 0.2, 0.3, 0.25, and so on, right? But that is the only thing that plays a significant role among the value of the enthalpies you get. So once you have that, you get your H3, you get your H4. It means you fulfilled all the values of the enthalpies that governs the cycle. Now, the next question now is, how then do you start treating your questions? You can be asked to find the network. Your first question could be, what is a network? Network is simply equal to the positive work, the sum of the positive work and the negative work. So WP plus WN. The sum of the expander work and the pump work gives us our network. It's as simple as this. So if I know the value of the pump work, which is the negative work, and I know the value of the positive work, which is the expander work, sum them together, that gives us our network. That could be the first question you'll be asked. The next question could be, what is the efficiency? Efficiency of the cycle. Efficiency is simply network divided by heat supplied. Okay, the heat supplied now multiplied by 100%. Heat supplied now is the heat from the boiler. I will find that here. Heat supplied, which is simply was H2 minus H1, right? So if I know the heat supplied, I know my network from this equation, then I can simply compute my efficiency. It's as simple as this. The next question could be, calculate the specific steam consumption. Specific steam consumption is simply the ratio of 3,600 divided by network. Okay, so specific steam consumption is simply 3,600 divided by network, and the unit is in kilograms per kilowatt hour. That's the formula for the specific steam consumption. And the next question you might likely be asked is to find the work ratio. So your work ratio is simply the ratio of the net work to the positive work. Okay, so you might likely want to multiply this by 100% just to convert it to percentage, since it's a ratio, if you wish. It's not a must anyways, but the work ratio is simply net work to the positive work, which means the net work obtained here divided by the expander work, because the expander work is a positive work. So these are the few questions you might likely be asked on a Carnot cycle. Now keep in mind that you can only employ these formulas if what is given to you as a Carnot cycle problem involves only two pressures, the first pressure and the second pressure. But if your question involves two temperatures, the first temperature and the second temperature, then the formulas is going to be different. In the next video, I'm going to be showing you how to derive the isothermal efficiency of a Carnot cycle. That involves just temperatures, the initial temperature and the final temperature. I'm sure you want to be a part of that video, so do well to smash the subscribe button right now and turn on your bell notification so you don't miss out on that video when it drops. In the meantime, do well to like this video, share to your friends, comment nicely. I will see you in the next video. Cheers.